Parts of a circle. We back in chapter 1 or 2, I can't remember which chapter it was. We talked about by definition what a circle was. A circle is the locus of points that is a set distance from a given point. If I say I draw all the points that are 7 inches from that dot, it's a circle. Okay. A circle is a set of all points in a plane that are equidistant from a given point called the center. Okay, so that would be the center of your circle there. A circle with center P is called circle P, or there's the actual figure for it. You draw a circle with a center and then P. The distance from the center to a point on the circle is called the radius. If two circles are congruent, they have the same radius. That's what makes them the same. You already know that. All the way across the circle, the diameter. Please know the difference between a radius and diameter. The terms radius and diameter describe segments as well as measures. A radius is not only a segment, but it's also the distance from the center to the outside. That's what we mean by radius. I could say the word radius for both the distance or the actual line segment. Angles and arcs. A central angle. A central angle of a circle is an angle with a vertex that's at the center. There's the vertex of that angle. Its sides contain 2 radii, and radii is the plural for radius. Its sides contain 2 radii of the circle, so angle ABC here is a central angle because it's comprised of 2 radii, and its center is the center, or its vertex is the center of the circle. We measure circles, or we measure angles, actually based on circles. A degree is actually 1/360th of an entire circle. So all the way around a circle, we know if we're talking about central angles, if we're going from here to here, or actually if we're going from here all the way back to here, a complete rotation in a circle is 360 degrees. And we've already done that. We dealt with vertical angles. Does everybody see the circle there? From here to here, well, that's the same thing as from here to here. These two were supplementary, right? You also have these that were vertical there. In a complete rotation, you have a 180 and another 180, or 360 total degrees in a rotation. And that's what we have here. The sum of the measures of the central angles. There you have angles 1, 2, and 3, which are all central angles. If you add up 3 central angles in a circle, you will always get 360 degrees. One complete rotation. Angle 1 plus angle 3 plus angle 2 there would give you a full rotation, or 360 degrees. It's funny, I actually talked about nearly this exact same topic this morning in pre-calculus. We got into reference angles and rotation angles and stuff like that, and you deal with the exact same material in pre-cal. Find the value of x. Let me blow it up. Find the value of x. Here we have a 130 degree angle. Here we have a 90 degree angle. Somebody add those two up for me, please. And you have what left? 140 degrees. And you can see that's fairly well drawn to scale. That's pretty close. So that's a 140 degree angle. The three angles, or excuse me, the angles that comprise a circle, the angles, central angles that make up a circle, always add up to 360. A couple more of those. Try the first one for me, Hunter. You have a 145 degree angle, you have a 165 degree angle. We add those two together, we get what, Hunter? $310 or so. So that leaves us with how many degrees? So that's my 50 degree angle. Any questions, bud? On the second one, Jagger, we have an 85, a 40, a right angle. Add those three up for me, please. No, not yet. Just the 85, the 40, and the 90. What'd you get on that? And then the 90 would be 215. Now we have a total of 360, so Dylan C. What's that leave for X? If those three add up to 215? That leaves how much for X? Yeah.
I'm not sure.
Right, 145 degrees. 360 total degrees. That was 215 of the 360. Take the 360, take off the 215, you're left with 145 degrees. Any questions? Next one, an arc. Again, talks about the same thing in pre-calc. An arc is a portion of a circle defined by two endpoints. We're not talking about all the way around the circle. We're talking about a portion of it. Okay. An arc is a portion of a circle defined by two endpoints. A central angle separates a circle into two arcs. Y'all see that? Related to the measure of the central angle. Let's talk about these two arcs. The red arc is what's called a minor arc. The reason it's a minor arc, and we'll get into this word, like, well, you already know it, so I can throw it out there. Does everybody know what a semicircle is? Cut it in half, right? A minor arc is smaller than a semicircle. If this angle is less than 180 degrees, because it's straight across, that'd be a semicircle. If an angle is less than 180 degrees, it'll cut off a minor arc. So therefore, here we have a minor arc, which would be my red arc. And does anybody want to take a stab at what they think the blue one's going to be? It's a major arc. You have minor arcs and you have major arcs. Major arcs are bigger than semicircles. Minor arcs are smaller than semicircles. That's going to become important here in just a second when we start naming these things. So minor arcs smaller, major arcs bigger. And that's what we got here. A minor arc is the shortest arc connecting two endpoints. You see there, arc AB, and look how we name this. Arc AB. That's what you're going to call that. Because if you don't, think about this. If I say arc AB, I could be talking about this, or could I not also be talking about this arc? So we need a way to distinguish, am I talking about this one, or am I talking about this one? Okay, and here's how we're going to do it. That was a minor arc. Look at the major arc. The major arc is not called arc AB. You have to throw in a third point. Okay, the major arc would be marked ADB. Even if that D was here, you still call this AB. This would be arc ADB. That would be a major arc. So major arcs are named with 3 points. Minor arcs are named with 2 points. Then you have the semicircle, which is half a circle is 180 degrees. You can name, honestly, you can do it with 2 or 3. It doesn't really matter. But here they call it arc ADB because it is equal to half the circle there. Now let's talk about what else this is saying. A minor arc is the shortest arc connecting 2 points on a circle. The measure of a minor arc is less than 180 degrees. We know that. This is less than 180. And equal to the measure of its related central angle. Same thing here. The measure of a major arc is greater than 180 and equals to 360 minus the measure of its central angle here. Or here's how to remember, guys. If you're wanting the measure of an arc, if this angle here is 90 degrees, then this arc is 90 degrees. That's what it's telling you. If this angle here, okay, let's say that this angle is still 90. Lost my pen. Let's say that this angle is still 90. That makes this angle what? You would not deal with angles bigger than 180, have we? 270 degrees. There's 360 total degrees in a circle. If this is 90, that leaves 270 degrees for this angle here. That's bigger than 180. That's fine. So if this angle is 270, then this arc is also 270. To find the measure of an arc, you simply look at its central angle. Let's work some problems. It says GJ is a diameter, that's important, of circle K. Identify each arc as major, minor, or a semicircle, then find its measure. Riley, GH. Look, it's only got 2 letters. So is that going to be a major or a minor arc, Riley? GH.
Minor.
That's minor. That's less than 180. It's less than a semicircle. So not only do they say tell whether it's major or minor, then find the measure of the arc. Here's a reminder. Here's how you do it. Look at the central angle. If the central angle is 122, then the arc is what? 122. That's all you have to do. The arc and the central angle is going to have the same measure. Dylan B. GLH. Let's do it in a different color here. GLH. Dylan, is that a major or a minor arc? That's major. It's bigger than 180. Everybody good there? How in the world are we going to find the measure of that? Does anybody know what this angle here is equal to? If this is 122, what's this angle? Because that's the arc that we're talking about. What is this angle equal to? 360 minus the 122, which is 238. So therefore, the measure of GLH is 238 degrees. Any questions there? Carly, GLJ. Find G, L, and J. What is that? It's a semicircle. You'll see that? It's half that circle. G to L to J. That's this portion of the semicircle. Actually, I think I lied to you a while ago. We're going to need three points for the semicircle as well. Because if I just say GJ there, it could be the top half or it could be the bottom half. So yeah, we're going to need to know the direction there. So GLJ would be the bottom half of that circle. It is half the circle. So therefore, it would equal 180 degrees. Angle GKJ is 180, and arc GLJ is also 180 degrees. That's enough of those. In the same circle or incongruent circles, two minor arcs are congruent. Let's stop there. The only way for this arc to be congruent to this arc, don't even try to, don't read the rest of it. Just tell me. The only way that arc FG could be congruent to arc JH there is if what's true? Angle 1 must be what? In order for the arcs to be congruent, the angles must be congruent. In order for the angles to be congruent, the arcs must. Do we not just know that? Example. If angle 1 is congruent to angle 2, if this angle is equal to this angle, does that not mean the arc is equal to the arc? If this angle is 50 and that angle is 50, then the arc's 50 and the arc's 50. The only way for two arcs to be the same is if the angles are the same. And vice versa, because look, if and only if. Do you remember the word that we use for if and only if statements? Mm-hmm. It's IFF was the abbreviation. There's the symbol we used for it. Starts with a B. It is a biconditional. A biconditional statement. That means it works forwards and it works backwards. That means if the angles are the same, then the arcs are the same. Which, by the way, notice what they do for arcs. They do an arc over the top. Or if the arcs are the same, then the angles are the same. It works both ways. Okay, biconditional statement. Refer to the circle graph. Now, this is going back, and this is just hitting on this. We're not going to spend a lot of time here because this is back 7th and 8th grade math. We're just going back to remind me. Before we start, though, 30% of 16. Trace, what's that word of mean? Times. It also means times if you're doing like 1/3 of 48. That word of, anytime you're dealing with percents, fractions, decimals, you're talking about that word of meaning times. So here we go. This problem says, let's undo that. That was bad. This problem says, find the measure of arc CD. The measure of arc CD. That's from here to here. When you're drawing a circle graph, okay, it says female participation in sports. 20% of the females, I don't know if this is a school, nationwide, I don't know, it doesn't say. 20% of them play basketball, 18% play track or run track and field, volleyball, 18%, softball, 16%, and so on and so forth. When you're doing a circle graph, not only does it represent this, but you know what? 18% of this circle is colored. This section is actually 18% of the whole circle. This section here is 20% of the entire circle. So you can go a step further. Here's the center. there's 360 total degrees. And also arc-wise, there's 360 total degrees. This section represents 20%. This section represents 18% of the whole thing. We will know the measure of arc CD. If there's 360 total degrees in that circle, find CD there. Volleyball, right? What percent? So will 18% of that 360 not represent that degree measure? 360 total degrees, 18% of it volleyball. So 18%, make sure before you multiply though, because all it means multiply, before you multiply you change this to 0.18. Change it to decimal point.
That's 64.8.
64.8, we'll call it 65 degrees. So this arc, and not only this arc, but this angle is equal to 65 degrees. Any questions? Measure of BC. Let's not work that again, right? What's the measure of arc BC? 65 degrees. It's also representing 18% of the circle, so 65 degrees as well. And if you found all those percentages, you can try it when you get home. If you do 16% of 360, you do 14% of 360, and you do it again, then you do 20% of 360, you've got all the angle measures. You should be able to add them back together and get that total 360 degrees. The arc addition postulate, that sounds familiar. Back in chapter 1, 2, somewhere in there, we had what was called the angle addition postulate. We had the segment addition postulate. The angle addition postulate stated if you've got an angle that's broken into two smaller angles, 1 and 2, that the measure of angle 1 plus the measure of angle 2 is equal to the entire angle there. Remember it? That was the angle addition postulate. Then you had the segment addition postulate, which said if you've got a line segment that's divided into smaller segments. Help me with the segment addition, Briley. It stated in this segment, in this line segment, what plus what would equal what?
AB plus BC plus AC.
Perfect. The two smaller segments add together to the whole piece. So, do you already know what this is going to say? Yeah. The arc addition postulate states here, the measure of arc XYZ. Measure of arc XYZ. And notice that's a minor arc. But is it okay that we call it XYZ? Do we know exactly? Yeah, go in that order. X to Y to Z. That's a minor arc. That's fine. The measure of arc XYZ is equal to the measure of arc XY, which is this small one, plus the measure of arc YZ, which is that small one. That's all the arc addition postulate states. Let's use it. Find the measure and circle F. The measure of arc AED. A to E to D. We're wanting the measure of that arc. Help me with this. Alex, first, tell me what's the measure of arc AE?
63.
Good. And what's the measure, Matt, of arc ED? So do you see that you can use the arc addition postulate there? What's the measure, anybody, of arc AED? 153 degrees. I'm in trouble today. 153 degrees. Now let's do the measure of arc ADB. Different color. A to D to B. A, D, B. That's a major. Good job. We have 63 and 90, but we've got some missing angles there. How are we going to do that? Let me. Which one's 90? Perfect. BCD is also 90 degrees. Do y'all see that? This arc will be a 90 degree arc. Wow. 180. So you tell me all that linear pair stuff and all that still comes into play when we're dealing with circles? Sure. Somebody tell me how big this angle is.
60.
It's 63 degrees. Wow. Vertical. Now we don't have to know that for this problem, but that is 63 degrees. You have vertical angle still applies. So A to D to B. So we have a 90 degree angle here. So that means we have a 90 degree arc. We have a 90 degree angle here, which means we have another 90 degree arc. So that'd be 180 and 63, which is a 243 degree arc. Good job. Any questions? I think that's the same problem. Moving on. Chords. Here's what a chord is. You got a circle. You have two endpoints that are on the circle, and you connect the dots, connect those endpoints. This is called a chord. Question. Is a diameter a chord? Yes. A chord is any line segment whose endpoints are on the circle. A diameter is actually the largest chord found in a circle. You can't get any bigger than a diameter. Okay. If you started dragging this down, it's going to get bigger, bigger, bigger until it hits the diameter. Then it's going to get smaller, smaller, smaller. Okay. A diameter is a chord. So let's talk about this theorem here. It's about chords. If the same circle or congruent circles, two minor arcs are congruent. Okay, minor arcs. Let's again talk about minor arcs. FG is a minor arc. JH is a minor arc. This is a pretty important theorem here. The only way for those two arcs to be congruent. Now, we already had one theorem that stated this. A while ago, we said the only way for those two arcs to be congruent is if this angle and this angle here was congruent. Remember that? If those are congruent, then the arcs are congruent. But not only that, somebody's already said it. If those angles are congruent and those arcs are congruent, also, the chords are going to be congruent. The distance from here to here is going to be the same thing as the distance from here to here. If you wanted to prove that, I bet it has something to do with, watch this. Aren't those the same? How in the world do we know those are the same? One word. Does anybody know what that one word is? How do we know that those two line segments that I just marked are the same? How about the word radius? Yeah. So therefore, wouldn't that make those two the same? Are those two triangles the same? I believe they are by a side angle side. Correct? So would that not make the green parts the same as well by CBCTC? Sure. That would be the proof of this theorem. So if, in essence, here's what you've got. If you've got two central angles that are the same, then you will have two arcs that are the same, and you will have two chords that are the same. And that is interchangeable. You can go in any direction. And there's the proof of that. I think that I kind of explained that beforehand, so we'll just skip over that. So here we go, all you embroidery fans. In your embroidery hoop here, AB and CD are congruent. AB is a 60-degree arc. CD is a 60-degree arc. That's pretty easy, right? If you have congruent chords, you will have congruent arcs. Think about it. Watch this, guys. Draw a chord. Draw another chord that's the same. What happens as you start moving this chord farther away? It gets bigger. Can y'all picture that? So if they're the same distance away, if the distance from here to here is the same, then these arcs will also be the same. It's fixing to lead us into another theorem that actually connects right along with that too. In these figures, and notice you've got two congruent circles. It doesn't just work only with the same circle, but if the circles are the same size, it'll work again. You have two congruent circles, J and K are congruent. MN and PQ are congruent. So since the chords are congruent, since the arcs are congruent, the chords are congruent. So therefore, 2x plus 1, finish the equation there for me. And we do that in our head, don't we? Move our x's to the right, move our numbers to the left. What's x? Perfect. So my chord lengths are 17 and 17 if you want to check that. Questions? Oh. Here's that next one that I said. We're getting a lot done today. These are, well, we're nearly halfway done with the chapter. If a diameter of a circle is perpendicular to a chord. That's interesting. If a diameter or radius is perpendicular to a chord, then it bisects the chord and it bisects the arc. Let's draw that. You've got a circle. And I want you to kind of lead me through the explanation of why this is true. You've got a circle. The center is somewhere right in there. and you've got a radius or diameter that is actually perpendicular to a chord. It says if it's perpendicular, it's going to bisect it, and it's also going to bisect that, which that makes sense. If it's going to bisect this, then it's going to bisect this as well. How do we know that's true? If that's perpendicular, then it's going to bisect it. Huh? It will have 4 right angles, but it cuts it in half is what it's saying, that this and this is going to be the same. As just if it's perpendicular, it cuts it in half. Watch this, folks. If I drew a line from here to here, and I drew a line from here to here, first off, would those two lines be the same? Why? Because they are both radii. Correct? That's a radius, that's a radius. Those are the same. What kind of triangle is that? And you remember all that stuff we learned about isosceles triangles? And you're probably sitting there thinking, I thought we could throw that in the garbage. I didn't know that circles and isosceles triangles had anything to do with each other. Sure, they do. If you have these two radii, actually you're going to have tons of isosceles triangles, because if you're talking about central angles here, every triangle you draw that's a central angle is going to be isosceles. Does that make sense? Because all the radii are going to be the same. And if you have an isosceles triangle, do you remember the symmetry we talked about? You could cut that isosceles triangle in half, which is what you've done here. Everything on this side is going to be symmetrical to everything on this side. So will this equal this? Sure. Will this equal this? Yeah. Because if it's going to bisect the chord, it's going to bisect the arc as well. Okay. So let's scroll back up and see what our next theorem was. So the first theorem, if a diameter is perpendicular to a chord, it's going to bisect the chord. The second one says the perpendicular bisector of the chord, the perpendicular bisector of a chord is a diameter of the circle. That's actually pretty much just the converse of the first one. If you have something that is a perpendicular bisector of a chord, it will always be a radius or a diameter. Okay, that's just the converse of the first. Make sure that you have those theorems written down if you haven't already. So look at this. And on these problems, let's say we're finding P, let's see, measure of PQR is 98. And find PQ. PQR is 98. So here, around to here, ain't working. Here, around to here is 98 degrees. Y'all see that that's perpendicular? And like what I was going to get at, if you need to, just to where you can see it, draw this line and draw this line. And see that isosceles triangle there. Anytime you have an isosceles triangle and this is a perpendicular bisector, if this is 6, this is 6. If this whole arc is 98, how much is that a piece? 49 and 49. So therefore, the measure of arc PQ is 49. The measure of arc QR also 49 degrees. Okay. In circle R, find TVs. Anybody see a TV in there? I don't know. In circle R, find TV and round to the nearest hundredth. That's weird. Round to the nearest hundredth. It's got 5 and 6 in here. How in the world are you going to find TV and round to the nearest hundredth? Let's look at that. We're looking for the distance from T over 2 V. We're given that the distance from S to R is 6. The distance from U to S is 5. And we're looking for the distance from T to V. Okay, here's your tip. How far is it from R to V? How far is it? Let me draw another line here. That might help some. How far is it from R to V? Not 6. 6 is the distance from here to here. How far is it from R to V? Let me give you a hint. One word. Radius? 11. Y'all see now? If the distance from U to S is 5, the distance from S to R is 6, that means that whole distance is 11. Is that not a radius? Both of those are radius. So if this is 11, then this is 11. If this is a right angle, that means these lines are perpendicular, meaning that this is a right angle. Isn't that Pythagorean theorem? Wow. Even in circles, don't forget about Pythagorean theorem. A squared plus b squared equals c squared. To type that straight into your calculator, let's go ahead and move the 6 squared over. X squared is 11 squared minus 6 squared, so x would be the square root of that. 121 and 36. I don't know. Give me a decimal for it. Square root of 85, is that what you said? 9.21. So about 9.2. But yeah, unfortunately that's not my answer, right? Because it asked me to find TV. Now, can you multiply that by 2? A lot of people are saying, yeah, you can. Why? Let me remind you the theorem. If a radius is perpendicular to a chord, it bisects it. So that means if this is 9.2, then this is 9.2, and TV is 18.4. I thought it was 10. I don't know. If it was 100th, it'd be 18.45. Okay. Moving along. Here's the other one that I told you it leads into. You know this. Let me scroll down so before you see it, because I want you to tell me what's true here. I'm good at circles. If you got a chord and you've got another chord, and they're the same length, everything that we've learned so far, we're gonna combine all this stuff. If you have two chords that are the same length, if I drew central angles here, if the chords are the same, the central angles are the same. If the chords are the same, what about the arcs? The arcs are the same as well. Now here's your other theorem that goes along with it. How far are these from the center? Does that not just make sense? The distance here would be the same thing as the distance here. If you have two chords that are the same length, okay, then they have to be the same distance from the center. Two chords that are the same length. If you go out 3 inches here and draw a chord, now keep in mind when I say distance, it has to be perpendicular. And you go out 3 inches here and you draw a chord, those chords will have the exact same length. So here we go. So if two chords have the same length, their central angles are the same, their arcs are the same, and they are the same distance from the center of a circle. And here we have the biconditional that states that. Notice when I say biconditional, if and only if. It works both ways. Two chords are congruent if they're the same distance from the center. That's what equidistant means. And if they are the same distance from the center, then they are the same length. So here we go. Look at that funny looking shape. Now it looks crazy. Wx equals xy equals 22. Wx, xy are both 22. Let me write that down. I'll blow it up. Wx equals xy equals 22. So you have Wx, which is the chord here. You'll see that chord. Xy is this chord here, and they're both 22. Since those two chords have the same length, then what's true about the two distances from center? They're also the same. The distance from the center of the circle will be identical. Do you see how to set that up? Yeah. 5x has got to equal 3x plus 4, so x must be 2. You can plug it back in, that makes this 10, and it makes this 10. Is that a square? Man, all that stuff's starting to relate, isn't it? Because, well, I thought, well, two of the sides are the same. I thought that made it a square, because you also got two right angles in it. Would those two lines be parallel? Because if these two lines are parallel and these two lines, if we could prove that, then that'd be a parallelogram. And since that parallelogram has adjacent congruent sides, that'd make it a rhombus. Since it has a right angle, it'd make it a rectangle, which would make it a square. But could we prove that's a parallelogram? No. No, you can't. And I know why you're saying that, because you're sitting there thinking because it doesn't look like that. We're given that PQ is 3x minus 4. RS is 14. Write that down. PQ, I didn't separate these. PQ is 3x minus 4. And RS is 14. Find x. Let me take it, scroll over here and blow this up a little bit so we can see it better. There we go. You have noticed that these two chords are both a distance of 8 from the center. Did you see how I set it up? If two chords are the same distance from the center, those two chords must be equal in length. So therefore, PQ would have to equal RS. Find X, yeah. What about this, though? Let me ask you, this is extra information, but I just want to know. Is that a midpoint? Yes. If a chord is perpendicular to a radius, and I know this is not a radius, but if you want to keep drawing it, that's fine. Now it's a radius. If a chord is perpendicular to a radius, then it bisects it. So therefore, that would be a midpoint, and that would be a midpoint. You don't have to know that, but they are. So therefore, PQ, RS are the same. 3x minus 4 equals 14. Can anybody tell me what x is? Yep. X is 6. So therefore, the distance here is 14. The distance here is 14. If you wanted to know, the distance there is 7. The distance there is 7. Could I find the distance from here to here? No, not yet, because you actually don't know how far it is from here over to here. If you knew that distance, then yes, you could, because then you would have the length of the radius. Let's say that this was 2, then that would mean the radius is 10. That means that would 10, and, well, you could. You sure could. If I told you to find, we're getting deep now, ain't we? Watch this. If you know that that's 7 and that's 7, and that's 7 and that's 7, then you could draw a line here. Is that not Pythagorean theorem? A squared plus B squared. Somebody type it in. I'm just curious. A squared plus B squared equals C squared. So that's 7 squared plus 8 squared, and then take the square root of it, which is 10 points. So can anybody tell me how far it is from here to here? 2.6. Perfect. If the radius is 10.6, does that not make this radius 10.6 as well? The distance from here to here is 8, making that 2.6. Good job. Again, that was extra. I won't charge you for that one. Nearly done. Inscribed angles. We've talked about central angles. Now let's go to a second type of angles. We'll probably stop after we finish inscribed angles. See the difference? Angle QRS up there is an inscribed angle, not a central angle. A central angle has for its vertex the center. An inscribed angle, it has actually its vertex on the circle. QRS is an inscribed angle. The intercepted arc. Let's talk about what we mean by intercepted arc. If you draw that inscribed angle, think of it as being like Pac-Man. Okay, this arc that he's eating is called the intercepted arc, QS. So therefore, if QRS is your inscribed angle, then QS is your intercepted arc. That's going to be important to you. Let's look at this. You have a circle. Boom, right on. Here's the center. Blue one here, from what we just finished, is a central angle. Let's say that central angle is equal to 80 degrees. How big is the arc? This is your intercepted arc, right? Pac-Man's eating the intercepted arc. Your arc is 80 degrees. Now let's take those same endpoints and let's draw an inscribed angle. Question. Is it smaller? That was what I was fixing to ask. Is that inscribed angle the same as that central angle, or is it closed a little bit more? Now, a lot of people said, no, it's bigger. Look how much longer those legs are. And that's not what you're looking at. You're not looking at the length of the legs. You're looking at the opening. And my question is this opening the same or smaller than this opening? I think it's smaller, definitely. You know what the relationship is? There you go. If an angle is inscribed, then the measure of the angle is equal to half the measure of the intercepted arc. Makes sense. It's twice as far back. It's going to be half the size. And I bet we could use similar triangles to prove that. So let's say that arc AB here is, how big y'all think that arc is? Because here's your semicircle. Right? How big do you think that arc is? Just take a guess. 140? because this is 180, right? So I'd say that's about 140. So let's say that AB is 140 degrees. Now, if you were talking about the central angle would also equal 140, but since you're talking about an inscribed angle, how big is it? 70, half of it. An inscribed angle will equal half the intercepted arc. That's pretty easy, right? Here's your proof. Let's go through it. Let's see how they prove it. I told you I thought they might use similar triangles. I don't know. Probably not this one. No. Angle B is an inscribed angle in circle P. I want to prove that the measure of angle B is half the measure of that intercepted arc. Step number one, they don't start out with the given, do they? Because really you're not given much. You're given that's an inscribed angle. Okay. Step number one, it says draw an auxiliary line. Why can't you just draw a line if you want to? Because you can't. Between any 2 points, a line can be drawn between any 2 points. 2 points determine a line. Just because you can, right? If you have 2 points, can you draw a line between them? Yeah. Because that's all. If I say, well, here's point A, here's point B, draw a line between point A, there's only one line that you could draw. Okay. How do we know? How do we know that PB and PC are the same length? Look at your drawing. One word. Mm-hmm. They're both A's. Anybody know that word before? They're both a radius. They're both radii. All radii, and y'all haven't done that theorem yet, but do you know that's true? All radii of a circle are congruent. No matter where the radius is, it's going to be congruent to all other radii in that circle. So therefore, triangle PBC, Panama City Beach, no, that's PCB. Triangle PBC is isosceles. How do you know that's an isosceles triangle then? Do you find yourself saying because it just is? That's what an isosceles triangle is, right? Yep, definition of isosceles. An isosceles triangle has 2 equal sides. So by definition, that's isosceles. So since that's an isosceles triangle, the isosceles triangle theorem is going to say that 2 other things are also congruent. Since PB and PC are congruent, what else is congruent? Not by isosceles triangle theorem. Ignore everything else. You have an isosceles triangle here. This side is congruent to this side, and not only are the sides congruent, but the base angles are congruent as well. Measure of angle B equals the measure of angle C, right? The next step, this is a detailed proof. This is a tough one. I wouldn't do this to you. I'm not putting this one on the test. The measure of APC, everybody find APC, is equal to the measure of angle B plus the measure of angle C. Why in the world is that true? The measure of APC is equal to the measure of this angle plus the measure of this angle. Not necessarily. Because you don't know if that's 90. What type of angle? Y'all see the triangle there, right? What type of angle is APC? Is it on the inside of that triangle? Yeah. Do y'all remember what's true about exterior angles? Now, we went way out there for that part, didn't we? The measure of the exterior angle, good job, is equal to the sum of the measure of the 2 remote interior angles. So does APC not equal the measure of angle B plus the measure of angle C? Is that not what that says? And I believe that was called the exterior angles theorem. And then we can substitute in. Because look, didn't we just say, what's this? Didn't we just say that the measure of angle C was the same as measure of angle B? So can we not put measure of angle B right there? And say now the measure of APC is 2 times the measure of angle B. Where are we headed with that? The measure of APC is 2 times the measure of angle B. That's substitution. We just substituted in there, and then how did we go from there to there? That's substitution. Now we know the measure of arc AC equals the measure of APC. We've already done that. AC, why is arc AC the same thing as this angle? That's how you measure arcs, right? Definition of arc measure. And then they took and they substituted in. Since APC, whoops, let's not do that. There we go. Since APC is equal to this and APC is equal to this, then we know now that the measure of AC equals 2 times the measure of AB. They call that substitution. I don't. You know what I call that? Transitive. I call that the transitive property. And then they say, well, they just flip-flop them. That's the metric property. And then they divide by 2, and you now have, whoa, not that. By division property of inequality, you've got your formula. That was a long way to get there, but the measure of angle B equals half the measure of the intercepted arc. That's a tough proof. 10 steps, that's pretty nasty. Hey, look, it's a Z. Anytime I see Z's now, I'm thinking parallel lines, but this is not a parallel line problem. Find the measure of each. Find the measure of angle P. Hunter, is angle P a central angle or an inscribed angle? Everybody see that? All 3 corners are on that circle. So therefore, how do we find the measure of angle P, Hunter? Which is? Perfect. Inscribed angle, half the intercepted arc. PO now. We're going it backwards. Because now they give you, Jagger, notice this. The angle is half the arc. The arc is double the angle. So now they give you an angle, and they want to know what this arc is equal to. Jagger, if the angle is 56 degrees, how do we find the arc? The PO. The intercepted arc. Here's the angle. Do we take half of it, Jagger? If we're given the angle and we're looking for the arc. Okay, look at here. Here the angle is 35.
May I have your attention, please?
Here the angle is 35, the arc is 70. The angle is always half the arc. But if you're given the angle, anybody tell me what the arc is? 112. Because that's inscribed. If the angle is 56, double it and you get the arc. The arc is always double the angle is always half the arc. Are those lines parallel? Mm-mm. Why not? 35 and 56 have to be the same. Why? There you go. That's what I was looking for. Alternate interior angles must be the same. That was our bonus on the last test. Alternate interior angles must be the same. There, your alternate interior angles are not the same, so therefore those 2 lines are not parallel. Okay. Another one. I like these. Circles is one of my favorite chapters. I like the circle chapter. Find each measure. The measure of arc CL. It's Fantastic Four, right? You'll see that. CL. Anybody? Not 90. Because that looks like it, right? That's probably where most people are going to go. They're like, oh, that's the center of the circle, so since the center is 90, that makes the arc 90. But is that the center? And I'll prove to you in a second it's not going to be the center. How big is the arc? You remember all those problems where you had like 2 or 3 triangles into the same problem and you overlooked some of the triangles? I bet on this one you overlooked an inscribed angle. You see that? That 40-degree angle is an inscribed angle. All 3 of its corners are on the circle, so if the angle is 40, the arc is 80. So is this here a central angle? No. If that were a central angle, because that looks like 90 degrees, if that were a central angle, that should be the same as this, and it should be 90. No, that's not a central angle. This is not the center of the circle. What about the 98? How in the world are we going to find angle C? Same thing, guys. Look. To find angle C, let's try it. There's angle C that I'm looking for next. Is C an inscribed angle? Sure. So Dylan, C. How do I find angle C? How do you find an inscribed angle? So what's the arc equal to, Dylan? Pac-Man's eating what arc up there?
40?
No, arc. Careful. 40 is an angle. What arc's he eating? Here's his mouth. Here's the inscribed angle. He's eating what arc? Here's arcs.
98.
98 degrees. Your angle will always equal half the arc, so that makes it 49 degrees, right? Could we go further? Sure. 49 and 40. That's 89. How big is this angle? 91 degrees. That's nearly a right triangle. So therefore, nearly in the center, isn't it? So if that's 91, then this is 91. If those are 91, then both of these are 89. Because, hey, isn't that an exterior angle? Two interiors, 89, 89. Could we use this 91 and say this is 91? No. This is not the center of the circle. That's not a central angle.